Swayam Prabha. Digital India. Educated India.
Okay, let's get started with today's class, right? So, what we are going to do today is to learn about what is called as the state space representation. Okay, so this is like an alternative representation of the class of dynamic systems that we are studying. So, this course is more towards analyzing systems when we represent them using what are called as transfer functions, right? So, the state space representation is another commonly used method to essentially do the same thing, right? So, as what we are doing with transfer function. So, but then the main difference is that like we stay in the time domain, right, rather than going to the complex domain as we do when we talk about the transfer function of the system. Okay, so let's learn what this is and then like how one can get the state space representation and in a certain sense how is it equivalent to the transfer function that we have been looking at. Okay, so let's start with an example so that like just we continue from where we left off, right? So let's say I have a mass spring damper system, you know, like which we already are familiar with, and we already know that the governing equation of the mass spring damper system is going to be mx double dot plus cx dot plus kx equals f of t. Okay. So, for this system or plant the input is the force f of t which we give to the mass. Let us consider that the output of the system is the displacement x of t. Okay. So, that is my input output as far as this particular system is concerned. And we have already derived its transfer function. The plant transfer function was the Laplace of the output by Laplace of the input when all the initial conditions were 0, and we already know that for this particular mass spring damper system the transfer function is 1 divided by ms square plus cs plus k. Okay. So, all this is something which we already are aware of. Okay. So, now what is this state space representation? So, the basic idea behind the state space representation is to rewrite a nth order ODE meaning ordinary differential equation, right, as a set of n first order ODEs. Okay. So, that is the basic idea, right, behind the state space representation. So, you give me a nth order ODE, can I rewrite it as a set of n first order ODEs? Okay. So, that is a question we are going to ask ourselves. Okay. So, the answer is it is possible. We are going to see how. So, to essentially do that we define we need to first define what are called state variables. So, what are state variables? Okay. So, for example, let me give an example. Let us say in this mass spring damper system, you know, I can consider the displacement of the mass and the speed of the mass as state variables, right? Because let us say suppose someone gives me information about the displacement of the mass and the speed of the mass at each and every instant of time, I would be able to completely characterize what is happening to that mass, right? So, in a certain sense state variables are those variables whose knowledge at each and every instant of time can completely characterize that system. Okay. So, that is the what to say notion of state variables. Okay. So, let me write that definition down. So, state variables are those variables whose knowledge at each and every instant of time is sufficient to completely characterize the system under study. Sufficient to completely characterize the system or plant. Okay. So, that is the definition of state variables. Okay. So, as we discussed, in this particular mass spring damper system, I could take the displacement of the mass and the speed of the mass, right, as the two state variables to characterize the system. Okay. We are going to use that to our advantage. As you go deeper, like I am only going to give you a broad introduction to state space representation. In advanced courses and controls, like you would go deeper into state space representation, and where we would realize that the state space representation for the same system can be non-unique. Okay, and by and large, like that is used to our advantage when we do analysis. Okay, so all these factors, like would be further studied when you go to advanced courses. Okay, but I would briefly touch upon those once we complete our analysis today. Okay. So, so how do I get the state space representation of this system, right? So, the main step is select. Okay. So, if I want to essentially write the governing equation of any system in the state space representation, what do I do, right? So, first thing is that select n state variables. Okay. So, because in general we are dealing with a nth order system, right. So, the question is what am I answering as far as these steps are concerned. The question that we are asking ourselves is that how does one represent a nth order system in the state space form. Okay, so that is the question that we are asking ourselves, right? So let's say we already know how to represent in the transfer function form, right? So we are giving an nth order system for the class under study. Like we know that we can characterize it as using an nth order linear ODE, right, with constant coefficients. Then we take Laplace transform, then substitute all initial conditions to be 0, then we get the transfer function of the system. Okay. So now the question that we are asking ourselves is that, like, how can I do the same thing as far as the state space representation is concerned. So you are given a nth order system. The first step is to choose n state variables, right? So second step is that so write n first order ODEs, each one characterizing the time evolution of the n state variables. Okay, so that is the second step. Okay, so we have n state variables. What you do is that, like, essentially you essentially write down n first order ODEs, each one characterizing the time evolution of each state variable. Okay, we will understand what it is shortly. Okay, so and then, like, we collect them. Okay, and in fact the main mathematical tool which will be useful in the state space representation or analysis using state space representation is linear algebra in general, right? So that's why, like, a good working knowledge of linear algebra is important. Okay, so if you want to work with state space representation for transfer function, we needed a good working knowledge of Laplace transform on complex variables, right? For state space, we need a good understanding of linear algebra. Okay, so to work with, see, we'll see why, right? So let's go back to to our example. Okay, what we do is that like we essentially select two state variables. Why am I selecting two state variables? Because the value of n is 2 here, right? So for our mass spring damper system, the value of n is 2, right? So that's something which we already know, correct? Yeah. So I have to select two state variables. So by and large, state variables are denoted by the character x. Okay. So let the first state variable x1. Okay. Please don't confuse this x with the displacement x. Okay. So in by and large is a convention to write the state variable using the character x. Okay. So the first state variable x1, let's take it as the displacement x of t, right? And let's say the second state variable x2, let us say we take it as the speed x dot of t. Okay, so let's say we choose these two as the state variables, right? So then we can immediately observe that x1 dot t, okay, which is the first derivative of the first state variable x1, right? That's going to be equal to x dot of t, right? If I differentiate the first state variable, I am going to get x dot. But what is x dot? X dot is going to be equal to x2t, right? So the idea is essentially to write these time evolution equations in terms of the state variables themselves and the inputs. Okay, that's where we are coming to, right? So that's what we get from the first equation. I hope it's clear what I did, right? So I defined two state variables as the displacement x and the speed x dot, and then like what we are doing now is that like I am taking the first derivative of each state variable. Okay, so first derivative of x1 is x1 dot, that is x dot by our definition, and x dot is nothing but x2, once again by the choice of our state variables, right? Okay, then we have x2 dot. What is x2 dot? It's going to become x double dot. Okay, so now I need to rewrite x double dot, which is the acceleration, right, in terms of the state variables themselves, right? How can I do that? So of course I can't write it as x1 double dot, right, because what will happen if I do that, then the order of this equation will become 2, right? So the idea is to write what to say equations like which characterize the time evolution of the state variables in terms of first order ODEs, right? So how can I write for x double dot? I can use the governing equation, right? So you see, at some point we need to use the governing equation of motion, right? So see, how did we get the transfer function? The transfer function came from the governing equation of motion. We use the governing equation of motion for the system to derive the transfer function, did we not? Similarly, we have to use it for the state space representation also. So from the governing equation of motion, I can write x double dot as the following. I can write x double dot as minus k divided by m x of t minus c divided by m x dot of t plus 1 divided by m f of t. Am I correct? I just rearranged terms. Okay. So let me tell you how I got it. I use the governing equation of motion. So if I take cx dot and kx to the other side, you get a negative sign, and then you divide throughout by m. That's all I did. Okay. So very simple algebra. So if I do that, I get x double dot as minus k by m x of t minus c by m x dot of t plus 1 by m f of t. Now what is x of t? It is a first state variable, right? So I can replace x of t as x1t, okay, and x dot of t is going to be x2t, okay, and anyway f of t is the input, I retain it as it is, fine. So these two equations, equation 1 and equation 2, are the what we call as the two state equations. Okay. So what are these state equations? State equations are these first order ODEs that talk about the or characterize the time evolution of each state variable. Okay, so those are what are called as state equations. So that's what we talked about in the second step, right? So I told that we need to write n first order ODEs, each one characterizing the time evolution of the n state variables. What we have done is that we have written 2 first order ODEs, right, for this particular example. So those are what are called as the state equations. So state equations are essentially first order differential equations which characterize the time evolution of the state variables. Okay, that's the state equation. Okay, fine. Okay, so these two are the 2 state equations, scalar state equations here, right? Now what we do is that we define, let the state vector, okay. So some people call it as a state variables vector, or the state vector, or the vector of state variables. Okay, so depending on which reference you have different terms, but essentially what we have is that we have a state vector x of t. Of course, my notation is that like typically vectors are denoted by lowercase characters in bold font, right? So because since I can't write bold font here, I am putting a tilde underneath, okay, just to indicate that that quantity is a vector, right? So that is the notation I am following here. So let us say I choose the state vector as a column vector where I arrange the 2 state variables, okay, x1 and x2. Okay, so that's what I do. Okay, so I take the state variable vector as this. Fine. Now this essentially tells me that x dot, which is the first derivative of the state vector, right, is essentially x1 dot and x2 dot. Okay, that is nothing but something multiplying x1t, x2t plus something multiplying the input f of t. We will see that typically we can write in this form. Okay, let me show you how to write in this form. Okay, so what I have done is that I have collected the n state variables as a nth order state vector. Okay, so in general, the dimension of x of t is n, right? The dimension of the state vector x of t is n. Okay, so that's easy to see, right? Because you just arrange the n state variables. In this case, it's 2. Okay, we have 2 state variables. Okay, so now what is x1 dot? X1 dot is x2. So I can immediately say that I can write the first equation in this way, right? If I say, like in the first term which multiplies x1 and x2, let us say I write the first row as 0, 1, and in the term multiplying the input f of t, I write 0 as a first entry. If you do the algebra, do you get x1 dot to be equal to x2? We do, right? So the row 0, 1 multiplies the column x1, x2, you get x2, right? And 0 multiplying f anyway will not contribute anything additional, right? So we are getting the first state equation. Okay, so then how will I get x2 dot? I can rewrite this as minus k by m minus c by m and 1 by m, right? If I do this, can I get the second equation? I do, right? You multiply the second row with the column state vector, and then 1 by m multiplies f of t, you get the second equation. Okay, so this is what is called as a state equation. Okay, of course, we already defined what are called state equation, right? So what is called as a state equation? It's essentially an equation that gives me the time evolution. It's a first order ODE which gives me a time evolution of the state variables, right. But this state equation is a vector state equation, right, because my x is a vector, the state vector is a vector. So, this is a vector ODE, right. So, this is a vector ODE, right. So, that is what we have got as a state equation. Okay. So, in general what happens is that this column vector is my state vector x of t, okay, and that is typically multiplied by a matrix A, okay, which is called as the state matrix. So, in general the dimension of the state matrix will be n by n in general. The size of the state matrix would be n by n in general. Okay. So, for CISO systems, this vector is denoted by a vector B, which is called as a input vector. Okay. So, that is the input vector, which is denoted by lowercase b. Okay. So, the general state equation for a CISO LTI causal dynamic system is you get x dot, which is the state vector's first derivative, that is going to be written as axt plus b times ut. Okay, that is the state equation in general. Okay, so this is the state equation. Okay, so what does the state equation, like some points to note. State equation, please note that first of all it is a vector ODE, but a first order vector ODE, right. And what does it tell me? It tells me how the state vector would evolve with respect to time, okay, in relation to the input that we are providing to the system, okay, because x dot t is a time derivative of x, okay, that is related to the state vector itself and the input provided to the system. So, you have some initial condition for the state and you give me an input to the state system, sorry, then the question becomes, like what happens to the state variables, right, with time. So, that is what the state equation will tell me, okay, right. So, but we are not done yet, right, because ultimately, like for us, our visualization of a system or a plant is an entity to which we give an input and we get an output, right. We are not even looked at the output yet, right. So, this is the state equation, okay, this is only the first equation in the state space representation. Now, what is our output in this case? Let us say we call the output as y of t. For our example, the output is a displacement x, right. So, what is x in terms of the state variable? It is x1, correct. So, how can I get x1 from the state vector? Okay. So, in this example, my output is a displacement x, which is the first state variable. Suppose I want to generalize, right, and rewrite it as what to say, some function of the state vector itself, right. How can I extract x1 from the state vector x1, x2? If I take the dot product of 1, 0 with x1 and x2, do I get x1? Right? Correct? Do you agree? Okay. So, we immediately see that my output is equal to the first state variable in this example, which can be obtained as a dot product of a vector and the state vector. Okay. I choose the first vector 1, 0 appropriately, okay, depending on what my output is, right. So, since we are dealing with a linear system, the output is going to be a linear combination of the state variables. Okay. So, the vector which with which I take the dot product will be appropriately varying. In this example, it's 1, 0. Okay? So, this is what is called as the output equation. This vector is denoted by a vector C, which is called as an output vector. Okay, and this is my, anyway, my vector x of t, right. So, this equation is what is called as the output equation. Okay. This is what is called as an output equation. So, similarly, the general output equation for a SISO LTI causal dynamic system is going to be y of t is equal to c dot x of t plus dut. What is this dut? C dot x of t we have already seen, right? C is the output vector, x is the state vector. What is this dut term? Dut is what is called as a direct transmission term which comes in the output equation when m is equal to n. Okay? We get this term when m is equal to n. Do you remember what are m and n? If you recall the general governing equation of the class of system under study, the ODE, n was the highest, n is the highest derivative of the output term on the left hand side, right? M is the highest derivative of the input term, right? So, in this example m is 0, n is 2, so we do not get a direct transmission term in the output equation for this example, but in general this is going to be the output equation, right? Y of t is equal to c dot x of t plus d times u of t. Okay, that is going to be the equation in general. Of which one? Direct transmission term, because typically what will happen is that when you have m is equal to n, the state vector will be affected by the input that you are getting, but the output term in addition to being influenced by the state vector, there will be one component which will be directly influenced by the inputs. Okay? So, we will do an example. Okay? I will maybe give you an example so that you can understand it better, right? See, what is going to happen is that if you are having m equals n, think about the transfer function approach, right? So, we did not do any case where m is equal to n yet, alright, but let us say if m were equal to n for any transfer function, what do you think will happen, you know, when you take the let us say partial fraction expansion and inverse Laplace transform, you will have one constant, right, which will come in, okay, because why? You are dividing, let us say in the numerator you had a second order polynomial, denominator also you will have a second order polynomial. If you recall division of polynomials, you can have a remainder, right, a quotient and a remainder, right, that quotient will be a constant, right, and then you will have a remainder. So, that quotient will automatically multiply the input. So, you will have one term which will directly come from the input, other term will be from the dynamics of the system. So, that is the physics, right. Similarly, here the direct transmission term will essentially imply the term that is directly affecting the output through the input, right, and c dot x comes from the dynamics of the system. Okay, so, that is the interpretation that we have. Okay. So, this is the output equation in general. Of course, at this point one aside which I should say is that like almost all textbooks, references in controls would write this output equation as y of t is equal to C transpose x of t plus du of t. Okay, because what they will do is that like they will take the output vector to be a row vector, so that like it's like a matrix operation, right? You multiply a row with a column and then you get it. Okay, you are free to choose any notation that you want to follow. So if you chose that notation, you know, like you will have C transpose to be 1 0. Okay, rather than I wrote it as a column vector, C as a column vector 1 0 and put a dot product. You know, like if you want to follow this notation, which is there in almost all textbooks for a CISO state space representation, you can also follow that. Okay, absolutely. D is a scalar for CISO system, right? Because ultimately we are dealing with a CISO system, right? So essentially y is a scalar. So obviously on the right hand side also you should have a scalar, right? So u is a scalar, so d is a scalar. Okay, and c is a vector, x is a vector. You take dot product, you will get a scalar, right? Scalar value function. So you can see that it's the terms agree dimensionally, right? So that's something which is very important.